So if you build $1 million house, with pristine hardwood floors, gorgeous crown molding, and a flawless roof, but you don't really think about the dirt underneath it, you haven't actually built a fortress.
No, definitely not.
Right. You've basically built a highly detailed sandcastle at low tide.
That is a great analogy.
Because eventually, inevitably, the water is coming. And we so often forget that water is incredibly heavy. I mean, it weighs over 62 pounds per cubic foot.
It's massive. And when the soil around your foundation gets saturated after a big storm, that water doesn't just sit there.
No, it actively pushes against your concrete basement walls with thousands of pounds of pressure.
Right. Exactly. Engineers call it hydrostatic pressure. Yeah. And without a dedicated escape route, that water will literally find microscopic pores in your concrete.
Just forces its way inside.
Yeah, and it can eventually snap a foundation wall right in half.
Which leaves you with, a $50,000 repair bill?
Easily.
Yeah. So today, we are taking a deep dive into the invisible subterranean moat that stops your house from sinking into the mud. We're talking about the French drain.
It really is the unsung hero of modern infrastructure. I mean, we spend our lives looking up at the magnificent architecture of our cities, our homes, our bridges.
Sure.
But we spend almost no time thinking about the silent, buried engineering that keeps those structures from just washing away.
Yeah, it's totally hidden. So, for the listener who maybe isn't familiar, what fundamentally is a French drain?
Well, it's sometimes called a trench drain or a blind drain or even a weeping tile system. But it's an elegantly simple concept.
Okay.
It is basically just a trench dug into the earth filled with gravel, and usually it has a perforated pipe at the bottom.
Just a pipe with holes in it.
Right. And its entire job is to manipulate fluid dynamics.
Okay, how so?
By giving surface water and groundwater an unobstructed path of least resistance, it rapidly intercepts and redirects that water away from vulnerable areas.
Right, getting it away before that hydrostatic pressure can even begin to build up.
Exactly.
So it's basically a dedicated underground expressway for water.
That's exactly what it is.
Now, with a name like French drain, I think most people naturally picture some grand Parisian architectural innovation, right?
Oh, yeah, like the sewers of Paris?
Yes. You imagine it being developed alongside those famous vaulted sewers in the 1800s. But the true origin story completely caught me off guard.
It's pretty surprising.
Yeah, to find the beginning of the French drain, we aren't traveling to France at all. We're actually heading to 19th century America.
Yeah, the moniker is incredibly misleading. The French in French drain actually comes from a guy named Henry Flagg French.
Okay, who was he?
He was a lawyer and an assistant U.S. Treasury Secretary, actually.
Wait, really? A Treasury Secretary?
Yeah. He was a rather innovative thinker from Concord, Massachusetts, lived from 1813 to 1885, and he popularized this specific drainage system in a book he wrote in 1859.
Oh, the farm drainage book.
Exactly, titled Farm Drainage. He was just trying to solve the age-old problem of waterlogged farmland ruining crop yields.
I just love the idea of a Treasury Secretary from Massachusetts becoming the namesake for, one of the most vital pieces of landscaping engineering in the entire world.
It is pretty funny.
But looking at the blueprints for his original design from 1859, it was quite a bit different from the plastic piping we buy at the hardware store today.
Oh, totally different. French's original drains were made out of sections of ordinary flat roofing tile.
Like for a house roof?
Yeah. He would lay them down at the bottom of a trench, kind of creating a crude pipe, but he would purposefully leave a tiny 1/8-inch gap between the sections.
So the water could get in.
Right, to allow the water to seep inside.
And honestly, looking at that mechanic, I have to push back a little on the brilliance of this.
Okay, let's hear it.
Well, if you bury roofing tiles with a tiny 1/8-inch gap, and you completely surround them with wet dirt, wouldn't that just instantly fill with mud?
You would think so, yeah.
I mean, how does a buried gap not just become a clogged, useless mess after the very first rainstorm?
And that is the exact engineering hurdle Henry Flagg French had to overcome. The solution really highlights the sheer brilliance of 19th century construction.
How do they do it?
Well, if you just threw some tires in the dirt, you're absolutely right. It would clog immediately. It'd be entirely useless.
Right.
To prevent that, builders working back then, before the era of modern synthetic materials, had to perform this highly meticulous, agonizingly slow process.
Oh, they had to sort the rocks.
Yes. Manually grading the gravel they used to fill the trench. They didn't just dump a wheelbarrow of random rocks over the
Right,
tiles.
because that wouldn't filter anything.
Exactly. They specifically placed coarse, large gravel in the very center, directly against those 1/8-inch gaps.
Okay.
Then, they gradually used finer and finer gravel as they worked their way out to the edges of the trench. The gravel actually met the natural dirt.
Oh, wow. So they were essentially building a three-dimensional gradient filter by hand, like stone by stone.
A masterclass in natural filtration. And the exact sizing of these gravel particles wasn't random at all.
It was calculated.
Highly calculated. The gradient of the gravel had to be specifically contingent on the gradation of the surrounding native soil.
So a sandy soil would need a different gravel mix than clay.
Precisely. The sizes of the stones were critical because they had to perfectly lock together to create what we call macropores.
Macropores, which are just the tiny, empty void spaces between the particles of gravel.
Exactly. These voids had to be mathematically large enough to let water slip through with zero resistance, but physically too small to let the surrounding soil particles wash in.
That is wild.
If the builders got the math wrong or, rushed the sorting process, the soil would wash into the pores, migrate into the center, enter that 1/8-inch gap, and just destroy the drain.
Man. Hand sorting gravel by size, perfectly matching it to the local soil type, building a perfect gradient over hundreds of feet of trenching just to protect a gap in some roofing tiles.
It's a lot of work.
That is an agonizing, back-breaking amount of labor, which makes perfect sense why this system had to evolve.
Oh, absolutely.
If there's one thing engineers absolutely hate, it's inefficient manual labor.
They despise it.
They needed a way to keep the dirt out without hand-placing millions of tiny rocks. And I guess that brings us to the modern subterranean highway.
Yeah, necessity and material science really drove a massive leap forward here. Today, the agonizing hand sorting of gravel is entirely obsolete.
Thanks to fabrics, right?
Yep, the invention of geotextiles or landscaping textiles. Instead of relying on perfectly sized stones to filter the soil, modern builders wrap the entire system in this specialized synthetic fabric.
Both the pipe and the gravel, right?
Right, a uniform layer of gravel and the pipe, all wrapped up.
These are those tough, black woven fabrics you always see rolled out on construction sites.
That's the stuff.
If you look at them closely, they basically look like giant, heavy-duty coffee filters. And I imagine they work exactly the same way. The microscopic weave of the fabric physically stops the migration of the dirt.
They do, but they actually solve another massive subterranean problem too. Plant life.
Oh, roots.
Yes. Geotextiles don't just stop dirt, they act as a vital armor against root intrusion. Trees and large shrubs are incredibly aggressive when seeking out water.
They'll find it anywhere.
Anywhere. And without a geotextile barrier, tiny roots will sense the moisture in a French drain, grow right through the gravel, enter the pipe, and expand until they completely shatter the system from the inside out.
Yikes. So the fabric allows water to pass through freely while keeping the destructive elements, both soil and roots, firmly on the outside.
Exactly.
Let's look at the pipe itself, because this is where the actual transit happens. The modern term for this is a weeping tile, which is a wildly poetic name for a piece of corrugated black plastic.
It really is. It actually gets that name from the era when these drain pipes were manufactured from terracotta.
Oh, clay pipes.
Right. Terracotta is highly porous, so it would naturally weep or exude liquids through the clay itself. But today, we use plastic pipes with actual manufactured holes or perforations punched all the way around them.
The best mental image I have for this is a reverse soaker hose.
Ooh, I like that.
Like if you ever put a soaker hose in your garden, you hook it up to a spigot, and it slowly leaks water outward into the dirt to, water your tomatoes.
Sure.
A weeping tile does the exact opposite. Instead of spraying water out, it pulls water in.
A reverse soaker hose perfectly highlights the mechanics of percolation. Because a very common misconception is that this buried pipe is acting like an underground holding tank.
Like a giant buried barrel collecting rainwater.
Exactly. But in reality, the pipe's interior provides a very minor volume for actual water storage. That is not its job.
That's a highway.
Right. Its primary purpose is rapid transit. It provides a path of least resistance.
Because water always takes the easiest possible route.
Always. I mean, imagine the dense, hard-packed clay soil around a house. Water struggles to move through it. But right next to that clay is a trench filled with gravel, which is mostly empty airspace. And inside that is a completely hollow pipe.
So the surrounding saturated soil is under immense pressure, while the empty pipe is under zero pressure.
Exactly. The water naturally forces its way out of the dense soil, through the fabric, through the voids in the gravel, and weeps into the perforations of the pipe, seeking equilibrium.
And once it's inside,
Once inside, the subtle gravity drop of the trench takes over.
they slope the trenches, right?
Yeah, typically dug with a precise slope of 1 in 100 to 1 in 200. And that slope turns the pipe into a high-speed expressway discharging that surplus water.
This is where the engineering gets incredibly clever, I think, because water behaves very differently depending on the landscape.
Oh, absolutely.
The fluid dynamics of a sloping, rocky hillside in the Pacific Northwest are going to demand a very different approach than, say, a perfectly flat, sandy suburban backyard in Florida.
Right, you can't use a one-size-fits-all approach.
Because of this, engineers couldn't just stick with one basic trench design. They had to adapt, creating a whole fascinating array of specialized variants.
And the adaptability of the French drain is exactly why it's so ubiquitous. Consider the aesthetic problem of a pristine landscape, like a high-end golf course or a luxury estate.
Yeah, you can't have ugly, exposed gravel trenches crisscrossing the fairways.
Exactly. That specific challenge birthed the curtain drain. This is a stealth version of the system.
How does it stay hidden?
Well, while a traditional French drain might have gravel coming all the way up to the surface to catch surface runoff, a curtain drain stops short. The gravel and pipe are buried deep, and the top of the trench is covered over with native soil.
Allowing you to plant pristine turf grass right over it.
Yes, the drain pulls the deep groundwater away invisibly, leaving the surface looking completely untouched.
Okay, but what if your biggest problem isn't hidden groundwater, but massive amounts of surface water?
Like a flood zone.
Right. Let's say you live at the bottom of a hill, and every time it rains, a river of water, dead leaves, and mud comes rushing into your yard. A hidden curtain drain wouldn't catch that surface flood fast enough.
No, it wouldn't. For that, you'd use a collector drain. This is a hybrid model that pulls double duty.
It catches both.
Yeah, it intercepts the deep groundwater, but the gravel also extends all the way to the surface to swallow that rushing surface runoff.
But wouldn't it fill with trash?
Good point. Because it's exposed to the surface, it features a cleanable filter at the top. This ensures that the dead leaves, twigs, and surface trash don't migrate down into the subterranean highway and clog the pipe.
Okay, that makes sense.
And then there is the inescapable reality of construction budgets.
Oh, digging is expensive.
Digging a massive wide trench and filling it with tons of imported expensive gravel is incredibly costly. So to solve the cost issue, engineers developed the fin drain.
The fin drain?
Yeah, it is a brilliant piece of geometry. It still uses the subterranean perforated pipe at the bottom, but instead of a wide trench full of aggregate, it features a very thin, narrow vertical section of aggregate extending perpendicularly upward from the pipe.
Like a shark fin.
Exactly. This vertical fin is typically about 200 millimeters or roughly 8 inches tall. It acts like a vertical antenna sliced into the earth.
Oh, I see.
It catches the lateral movement of water in the soil and drops it straight down into the pipe. It requires a fraction of the digging and a fraction of the gravel, making it a highly economical alternative.
I follow the logic on all of those variants,
Mm-hmm.
but there is a specific configuration we need to unpack because it initially made no sense to me.
Oh, which one?
Well, depending on the expected volume of rainwater, engineers will sometimes install 2 or even 3 parallel underground drain pipes inside the exact same trench.
Ah, yes.
When I saw that, my immediate reaction was, isn't 3 pipes for one trench serious overkill?
Yeah.
Like, if you have that much water, why not just bury one giant oversized pipe and call it a day?
It absolutely sounds like overkill until you look at the brilliant physics of load balancing.
Okay, walk me through it.
Imagine a scenario where a drain is placed right under a massive commercial roofline or at the base of a steep concrete driveway. During a torrential downpour, that single pipe is going to receive a violent, massive volume of water incredibly quickly.
Sure, a ton of water all at once.
If you only have one pipe, even a very large one, and it overfills even for a moment, it loses its upper airspace inside the cylinder.
Wait, why is that upper airspace so crucial for moving water?
Because of friction and vacuum pressure. When a pipe completely fills with water, air bubbles get trapped inside.
Oh, like when you chug a bottle of water and it glugs.
Exactly. Without a continuous channel of air at the top of the pipe to allow the fluid to breathe and flow, those trapped air bubbles actually act like physical blockages.
They slow the whole thing down?
They create friction, and the flow of water violently chokes and slows down. But if you install multiple parallel pipes in the same gravel bed, you introduce redundancy.
So he share the load.
Right. When the first pipe closest to the deluge gets dangerously full, the excess water simply bypasses it, seeping sideways through the gravel macropores into the second parallel pipe.
Oh.
This ensures that no single pipe ever completely fills up. The vital airspace is maintained across the system, and the drain never chokes.
It is exactly like adding extra lanes to a highway to prevent a traffic jam. The water simply changes lanes when things get congested.
That's a perfect way to visualize it.
That makes perfect sense. You're maintaining the aerodynamics of the water flow. So this system has successfully collected the water, load balanced it across multiple pipes, and diverted it at high speed down a subtle gravity slope.
Yeah.
Where exactly is all this water supposed to go?
Yeah.
We've built an incredible subterranean highway, but where is the exit ramp?
Well, the terminus of a French drain is just as heavily engineered as the collection point.
Okay, what are the options?
The simplest exit ramp is an outfall onto a natural downhill slope, letting gravity safely dump the water far away from the foundation.
Just daylighting the pipe.
Exactly. But if you are in a flat suburban area without a convenient hillside, the system will often terminate in a dry well.
What's that?
This is essentially a deep, engineered pit lined with porous fabric and filled with rocks, designed to hold the massive volume of water temporarily while it slowly percolates back into the deep earth, far below the foundation level.
My favorite terminus by far, though, is the rain garden.
Oh, those are beautiful.
You're basically feeding a curated wetland with your roof runoff. You route the pipe into a specially designed, shallow depression in the yard planted with deep-rooted, water-loving native plants.
It's so efficient.
The plants actively drink up the excess water and filter it naturally. It is a brilliant ecological solution, especially in areas where municipal storm drains are overwhelmed.
Absolutely.
But this brings us to the reverse application. And surprisingly, as we look at the destination, we also uncover how this exact same technology is used in completely the opposite direction.
Yeah, the versatility of the underlying engineering is remarkable. We have spent this entire deep dive talking about weeping tiles acting like vacuums, collecting water and moving it away.
Right.
But in the world of septic systems, these pipes are used for the exact opposite reason.
How so?
Well, in a rural setting without city sewers, a home relies on a septic tank. The tank separates the heavy solids from the liquid waste.
Okay.
That remaining liquid, the clarified sewage, has to go somewhere to be naturally treated by the earth. So it is pumped out of the tank and fed into a network of shallowly buried weeping tiles spread across a large area known as a septic drain field.
This is where my reverse soaker hose analogy gets flipped right back around to just a regular soaker hose.
Exactly.
Instead of pulling liquid out of the dirt, the weeping tile is actively spreading the clarified sewage outward. It takes a concentrated volume of liquid and disperses it evenly throughout the massive drain field so the microscopic bacteria in the soil can safely break it down.
It is exactly like exhaling instead of inhaling.
That's a great way to put it. You're using the exact same anatomy, the trench, the gravel, the perforated pipe, the geotextile fabric, and the exact same fluid dynamics, but utilizing them to evenly distribute liquid outward rather than collecting it inward.
The core mechanism of managing subsurface liquid migration does not change. You see this exact reverse engineering in agriculture as well.
Oh, do farmers use this?
They do. To circle all the way back to Henry Flagg French, farmers today still tile their fields. They bury massive grids of these perforated pipes beneath hundreds of acres of
To
cropland.
dry them out.
Usually, yes. If the spring brings too much rain and the fields are waterlogged, the pipes act as traditional French drains, pulling the water away so the crops don't drown.
Right.
But during a severe summer drought, farmers can actually pump water into the tile system, using it to water the crops from the roots up.
Oh, that's incredibly smart.
Whether you are drying out a farmer's field, pulling hydrostatic pressure away from a basement, or distributing wastewater into a septic field, the physics of the weeping tile remain constant.
Moving massive amounts of water around sounds incredibly efficient, but it brings up a huge real-world complication.
What's that?
You aren't just moving pure distilled water. A high-speed underground expressway is going to carry whatever happens to be swept along for the ride. And anytime you start rapidly moving massive amounts of resources and potential pollutants across property lines,
Yeah.
you're going to catch the attention of the government.
And for very good reason. These private engineering projects inevitably intersect with public infrastructure and natural ecosystems.
Do you need permits for this?
Oh, yeah. In the United States, municipalities routinely require homeowners to pull specific permits before installing major drainage systems. This isn't just bureaucratic red tape, it is tied to federal environmental law.
Okay.
Any water that is artificially routed into public storm drains or natural waterways must be free of specific contaminants.
I can hear the collective groan of listeners right now.
It's the
Classic homeowner frustration. Like, listen, it is just rain falling on my own private grass. If I want to stick a pipe in the ground and shoot that rainwater into the street or the ditch behind my house so my basement doesn't flood, why does the government care? It's just water.
It is never just water once it hits the ground. This is where the environmental stakes become very real. A French drain, especially a collector drain taking in surface runoff, doesn't just move rain.
It takes everything else with it.
Exactly. Without proper geotextile filters or catch basins, these high-speed systems will transport motor oil from your driveway, heavy lawn fertilizers, fine sediments, and non-colloidal particles straight into municipal systems.
And just to clarify the engineering jargon there, a non-colloidal particle is essentially just a fancy term for tiny bits of solid matter like fine sand, silt, or clay that don't dissolve in water but are light enough to get swept along in the current.
Precisely. If your pipe is blasting a continuous stream of silt, fertilizer, and debris into a delicate downstream watercourse, you aren't just solving a puddle in your backyard.
You're passing the buck.
Worse, you are actively creating a localized environmental crisis. The silt chokes out aquatic life, and the fertilizers cause massive algae blooms.
Wow.
In the UK, local authorities enforce incredibly strict regulations regarding the specific outfall of any French drain into a ditch or stream for this exact reason. The law exists to mandate that your private subterranean solution doesn't become a toxic public disaster downstream.
It is all connected.
Yeah.
The water never just disappears. It always goes somewhere else. And the engineering of exactly how it gets there matters immensely.
It really does.
Which brings us to the end of our journey today. We have traveled all the way from Henry Flagg French's 1859 roofing tiles, meticulously packed with hand-sorted gravel, to the modern geotextile-wrapped, load-balancing, multi-piked expressways that quietly protect our daily lives. I mean, you've essentially earned an honorary degree in subterranean fluid dynamics today.
It's an amazing evolution. But I want to leave you with a final thought about where this invisible infrastructure might go next.
Oh, I'd love to hear it.
We've seen how French drains are masterfully designed to either push surplus water rapidly away from a structure or disperse wastewater evenly into a field. But as we look toward a future with rapidly changing global climates, a future where many regions might experience sudden, violent deluges of rain followed by agonizingly long, punishing droughts, the traditional concept of the French drain might need to evolve yet again.
How so?
Perhaps the future of this technology isn't just about treating water as a nuisance to be moved away to a terminus. Perhaps these massive underground networks could be adapted to act as decentralized subterranean reservoirs.
Oh, wow.
Imagine a system engineered to capture that massive stormwater runoff, but instead of dumping it into a municipal sewer, it banks that water deep beneath our yards, holding it safe from surface evaporation, ready to be tapped into when we desperately need it during a drought.
Turning the escape route into a vault. I absolutely love that concept. So, the next time you're walking through your neighborhood and you admire a perfectly flat, pristine green lawn, or a beautifully landscaped retaining wall, or a vibrant rain garden, I want you to look at it differently.
Yeah, it's not just dirt and grass.
Exactly. Remember that you aren't just looking at dirt and grass. You are standing directly above a hidden, silent highway of weeping tiles, working tirelessly, just inches beneath your feet to relieve the pressure and keep the whole world from washing away. Keep your sandcastles safe, everyone. Thanks for joining us on this deep dive.